The best way to learn data structures is not just by reading about them, but by seeing them in action. Understanding how nodes link together, how data flows through structures, and how operations are performed is much easier when we can visualize the process in real time. That's why we're bringing you this interactive visual demonstration, where you'll see linked lists and doubly linked lists come to life, how and elements are added, removed, and traversed. So let's dive in and break down linked lists in a way that makes learning simple, engaging, and intuitive. Let's begin. Data structures are the backbone of programming. Today we're exploring one of the most fundamental yet powerful structures, the linked list. But wait, what exactly is a linked list? And how does it work? By the end of this session, you'll not only understand linked lists, but also see them in action with animations that make everything crystal clear. So let's dive right in. What is a linked list? A linked list is a way to store data where each piece of data, called a node, is connected to the next one using a pointer. Unlike an array, where elements sit next to each other in memory, linked lists dynamically manage memory by storing scattered nodes, each linking to the next one. Let's think of it as a chain of people, where each person knows only the next person, but not the one before them. This is called a singly linked list. Let's break it down. In a singly linked list, each node has two parts. Value. This stores the actual data. Next pointer. This points to the next node in the list. The first node is called the head, and the last node is called the tail. If the list is empty, both the head and tail are null. But as soon as we start adding data, the nodes get linked. Now, let's start adding nodes to our list. If the list is empty, the new node becomes the head. Otherwise, the tail's pointer updates to link to the new node, and this node becomes the new tail. Let's see this in action. Watch as we add 1, 2, and 3 to our list. Now, let's remove nodes using the pop operation. If there's only one node, removing it makes the list empty. Otherwise, we find the second to last node and update its pointer to null, making it the new tail. Check this out. Each time we pop a node, the tail moves backward. Sometimes we don't want to remove a node. We just want to check the last value. That's where peek comes in. It simply returns the tail's value without modifying the list. Let's peek into our list now. What if we want to reset everything? By using the clear operation, we remove all nodes and set both the head and tail to null, emptying the list. Let's wipe the list clean and start fresh. Singly linked lists are great, but they have a limitation. We can only move forward through the list. But what if we needed to move both forward and backward? That's where doubly linked lists come in. Let's take a look. Part 2, Understanding doubly linked lists. What makes doubly linked lists different? A doubly linked list is just like a singly linked list, but with one key difference. Each node has 2 pointers instead of 1. A next pointer that links to the next node, a previous pointer that links to the previous node. This means we can traverse the list in both directions, making operations like deletion and insertion more efficient. Let's compare the two. In a singly linked list, a node only knows about the next node. In a doubly linked list, a node knows about both the next and previous nodes. This extra pointer allows us to move back and forth through the list. Let's add some nodes. Adding to the start, the new node's next pointer links to the old head, and the old head's previous pointer links back to the new node. Adding to the end, the new node's previous pointer links to the old tail, and the old tail's next pointer links to the new node. Removing nodes works just like before, but now we need to update both next and previous pointers. Removing from the start, move the head forward and set its previous pointer to null. Removing from the end, move the tail backward and set its next pointer to null. The best part about doubly linked lists is that we can move in both directions. Forward traversal. Start from the head and follow the next pointers until the end. Backward traversal. Start from the tail and follow the previous pointers until the beginning. Let's traverse the list forward and now backward. So, why do we use doubly linked lists? They make deletion and insertion faster, since we can access the previous node directly. They're used in music players, web browsers' back and forward buttons, and even undo-redo functions. They provide more flexibility compared to a singly linked list. And there you have it, the complete journey of singly and doubly linked lists. Singly linked lists are simple, efficient, and great for basic tasks. Doubly linked lists offer more flexibility and allow bi-directional navigation. Now that you understand how they work, try building one yourself. Experiment with adding, removing, and traversing nodes to see how these lists behave in action. If you enjoyed this breakdown, don't forget to like, share, and subscribe. Want to learn how event loops work in JavaScript? Then check out the video showing on the screen. See you there!